some very important in-person meetings are being organised right now. Take advantage of early bird registration rates, which are even lower if you're an Optica corporate member. Here's an overview of what's to come.
Optica will bring together the brightest and best in Los Angeles. Corner, New York, Brussels, Glasgow, Sunnyvale, Paris, and Malaga.
Got my shades in the lab about 10:15. White coat, cuff like a greaser again. Spinning that prism like a hubcap chrome, turning every photon into fuel I own. It's photonics. Baby, 2026. Riding down the light wave, doing new tricks. From the fiber in the ground to the chip in my hand, we make that sunshine jump on command. Yeah, photonics. Baby, 2026. Tiny little wave got on a thumbnail chip. Makes your eyes look slow and stiff. Lasers in the toolbox, markers on the floor, drawing up a future through a tiny door. It's photonics. They're upon a 26. Riding that light wave, doing new tricks. From the fiber in the ground to the chip in my hand, we make that sunshine jump on command. Yeah, photonics. Baby, 2026. From a single red dot on a dusty bench to a whole wide world in a data trench. Flip that switch, see the spectrum spin like a jukebox jumping when the coins roll in. Oh yeah! Baby, 2026. Riding that light wave, doing new tricks. From the
It all will happen here at IX Campus's castle of Saint-Germain-en-Laye in Paris. See you then.
photonics. shape the light. Cleaner cuts, smoother seams, big results from better beams. From tiny chips to medical tools, printing lines over precision rules. One small change in the beam you use can save you time you can't afford to lose. So come along on February 10. Join the Optica meeting online at 10. Hear what shaping a beam can mean for speed, precision, and everything between. If you work with lasers or just wanna understand why, come learn the art of shaping the beam. Come along on February 10. Come along on February 10.
有顾客。
What?
Okay, let's get started.
Hello, everyone, and thank you very much for joining the Optica online industry meeting on laser beam shaping. I'm joining from Vilnius, Lithuania. This is the heart of Europe, Central Europe, the capital, the world capital of laser. You can quote me on that. Vilnius, Lithuania is the capital of laser technologies. And I am really happy to join from Optica corporate member Optogama facilities. It's great to see the optical beam shaping technologies here. It was a fantastic meeting. Also today I went to see Optoman, great company as well. It was a great day. And there is no better way of doing a great day than to listen to that fantastic song to open the online industry meeting and also to hear the technologies and their needs of Lawrence Livermore, of Lasea, of Fraunhofer ILT, and of course of IPG. On the next 90 minutes, we're going to hear fantastic things from our integrators today. The meeting works like this, like you are used to the format. We have integrators and we have enablers. Our job is to make sure that the integrators share with us things that they need, their Christmas shopping list, and the enablers provide solutions that fulfill those needs. And the enablers are these people here, Kylabs, Asfericon, Hologram, Optoman, but also everyone here with me in the Zoom room. All of you should answer the Optica question, which is, of course, what can you do for the others and what can the others do for you? This is part of the program that we have for our Optica corporate members. This meeting is free of charge for everyone. And the reason for that is because we have Optica corporate members, such as, of course, Optogama, who pay very small membership fees and allow us to continue doing our job. So if you are in the meeting and you are not an Optica corporate member, please join and also understand that you're here because the Optica corporate members support us. This is also part of our series of online industry meetings. We have one every 2 weeks. Stay tuned for the one that happens exactly in 2 weeks from today, the Optica Global Advanced Manufacturing Alliance meeting. We have 2 meetings per year, one presence, one online. And this meeting is about talking about manufacturing technologies that are needed for the future of the optical industry. We focus on semiconductor manufacturing. So you have technologies for the semiconductor manufacturing industry. Write down 28 February, the Optica Global Advanced Manufacturing Alliance online meeting. And also, of course, for those of you who are going to OFC, don't forget to register to the Optica Executive Forum. And the week after OFC, we all meet at Corning, at the headquarters of Corning, in Corning, New York. I don't know if you have been there, but it's a unique experience. We go to the Corning headquarters to talk about advanced optics manufacturing. I hope to see many of you there, 24, 25 of March at Corning, New York. Please register online as soon as possible. We have limited seating. And also, I would like to remind everyone that this meeting is live streaming YouTube. So let me say hello to the YouTubers in the world over here. Hello, YouTubers of the world. If you have any questions in the meeting, please write them in the chat and I will read them in the room. And allow me to come back to the room and say to everyone, welcome to the online industry meeting. This meeting is going to be very unique. All of you use the chat to connect. Over the next 90 minutes, you all have to find suppliers, partners, and customers in the room. That's your task. And my task is to introduce our opening speaker today. I am really excited about this. For many years, we've been interacting with Lawrence Livermore. Since 3 years ago, we have been talking a lot about laser fusion with them. We have seen huge demand from high power laser beam shaping, and also we have seen huge demands and unmet needs from the semiconductor industry for manufacturing and inspection. Today, we have one of the group leaders of Lawrence Livermore with us, and the idea is to understand what John Hefner can do for us and what we can do for them. The floor and the attention of everyone, I'm really happy today, Helena. The floor and the attention of everyone goes to Lawrence Livermore.
Okay, can you all hear me?
Loud and clear.
All right. Let me get this in presentation mode. Can you all see that in presentation mode now?
Gorilla Glass clear.
All right. So hello, everyone. My name is John Hebner, and I'll be telling you about laser beam shaping on the world's highest energy laser system here at the National Ignition Facility at Lawrence Livermore National Laboratory. So since 1972 at Livermore, we've been using lasers to compress hydrogen to high temperatures and pressures, ultimately required to ignite a miniature star in the laboratory, or really a controlled nuclear fusion reaction, with applications for both national and energy security. Achieving the required energy, power, and beam control took 5 increasingly large and more sophisticated facilities to get there, with many improvements in lasers and optics technology, culminating in the NIF, which was completed in 2009 for the NNSA. 3 years ago, for the first time, NIF achieved controlled fusion in the laboratory. This was since repeated many times and now achieves a gain greater than 4, yielding about 8.6 megajoules of neutrons using its 2 megajoules UV drive laser system. Okay, so a key to the success of NIF was pushing the frontiers of laser beam quality and control. So the predecessor of NIF, or the prototype, was beamlet, and that modernized control at the 10 kilojoule class laser in terms of shaping the near-field beam profiles of their lasers, the wavefront through adaptive optics, the spectrum, and the far field through smoothing and phase plates. However, all these were static. So in 2010, NIF upgraded its beam control system to be programmable, mainly to shadow defects on the final optics and to flatten the beam fluence profiles and reduce intensity hotspots. This ultimately enables NIF to operate the UV final optics routinely above their damage thresholds. Okay, so let's see how this works. All right, so here is a beamline of NIF, and it starts with a master oscillator room, which creates precision sculpted seeds in time at the nanojoule level. And then those are injected via fiber into the preamplifier modules, or PAMs. Those amplify up to the 5 joule level. Those are then split 4 ways, and then they're injected into the main laser beamlines of NIF. These are 4-pass amplifiers, and they amplify ultimately up to 20 kilojoules or beyond. And then that gets converted in the final optics assembly to over 10 kilojoules in the ultraviolet. And then that gets focused onto the targets in the target chamber. Okay, so in 2010, we added a system that allows us to programmably alter the beam profile and optimize it ultimately for each of these beams. So the PSS, or programmable spatial shaper, uniquely creates these pattern profiles at the 1.8 centimeter scale. Here we can shape the beam profile, and we can add what we call spot or shadow blockers. So because this is a relay imaged architecture, a copy of that beam magnified by 20 times up to the 36 centimeter scale is now present at the final optics at high energy and high fluence. So this allows us to dial in the shape here in the low aperture, the low fluence part of the beam line, and then have that show up where we need it to protect these optics. Okay, so every laser shot on NIF can actually degrade the laser, and the degradation primarily happens at laser hotspots or optics flaws, and this system allows us to manage that degradation so that we can fully take advantage of all the energy that this laser can produce. You can also take that shaper and draw arbitrary profiles like leopards with all of their spots as well. Okay, so let's zoom in. I'll take you down into the preamplifier modules. So here's a regenerative laser amplifier, which puts out Gaussian beams. Those are then shaped into a square using a static mask. And then they go through an optically addressable light valve. This is the secret to this technology. And you can think of it as a giant pixel with analog shaping. And I'll dive into exactly how that works in a moment. So these were all created in collaboration with Meadowlark Optics based on our design. Okay, so the output of this creates our beam profiles with the arbitrary shapes, and that ultimately feeds into the beam path as I showed you on the previous slide. Okay, so let's see how this optically addressable light valve works. This is actually a fairly old technology. We have engineered it and scaled it up, and we continue to do so in a second generation. But here's the first generation that is currently online. So it works by taking a liquid crystal layer in series with a photoconductor. In our case, this was bismuth silicon oxide. And by applying a voltage across this sandwich, if you will, and also applying a blue address beam coming in here from right to left, wherever there is voltage and blue light, you are able to place an electric field across these liquid crystal molecules. So that when you come in with an infrared beam, in our case, what happens is if it's polarized, the polarization will chase the twist of the molecules. And if there is no blue light, there is no transmission. You get transmission only when there's voltage, blue light, and then ultimately that folds the liquid crystals in the longitudinal direction, disables their polarization rotation, allows you to get transmission past a series of wave plates and polarizers. Okay, so you can think of this as one giant liquid crystal that can be made with very high wavefront, very good wavefront, very good anti-reflection properties for the wavelength of interest, but it offloads the addressing, if you will, to an upstream pixelated ordinary projector. Okay, so now let's zoom back out and see how this system operates with the rest of the National Ignition Facility. Okay, so as I mentioned, we have these 48 programmable spatial shapers back at the front end, and they create these beams that are relay imaged to the final optics. And after every shot, we actually examine all of the optics in the final optics assembly. And with this camera, we're able to determine whether or not the optic is safe to continue firing, in which case it goes to the left along this loop. If it's not, it comes out and it can be often refinished and put back into service. We have an optical inspection system which identifies any flaws, particularly those that are growing with the high fluences present, and determines whether or not a blocker needs to be applied. In parallel, the laser performance operations model takes a look at the beam profile and determines whether or not there are any hotspots that need to be flattened. So the goal of this model is ultimately to take this distribution of fluence and cut off this high fluence tail. That high fluence tail doesn't do the optics any good, and it doesn't add much energy. But by cutting it off, we can extend the lifetime of those optics significantly. So this system ultimately mitigates the hotspots. It shields the optics, particularly at the few number of flaws, and enables NIF to continue operating safely at high energies. Okay, so fast forward to today. That old system, the first generation system, has been operating successfully for 15 years. Now we're working on a second generation system, and this will allow us to insert a shaper after those 1x4 splits so that we can individually address each of the 192 beam lines. Right now we only have 48 shapers, so the same pattern gets copied on 4 beam lines. With this second generation, we have to deploy this now downstream where the aperture is larger by a factor of 2.5 times. It goes from 2 centimeters to 5 centimeters roughly. And the fluence goes from a very low fluence of millijoules per square centimeter up to about a joule per square centimeter. So now this shaper must shape joule class beams directly. And this is something that you can read more about in some of the literature that I can show you down here by Brandon Buckley and Bikram Chatterjee. This new device, we have a prototype, and it's based on gallium nitride doped with manganese. And we are working on scaling the development of this up. And ultimately, we will be looking for partners, and we will put this out for bid so that we can build 192 of these. Okay, so in summary, Livermore and NIF continues to develop beam shaping capabilities to add powerful new functionalities to our high energy laser beams. Passive spatial shaping masks have made these high energies possible in the past. The first generation programmable shapers allowed us to maintain sustained high energy operation for the past 15 years and contributed to the ultimate achievement of fusion ignition in the laboratory. The second generation that we're working on now will enable us to even push those limits further. And ultimately, we'll be looking forward to partnering with someone. The spin-off technologies, of which there are many, include patterning of high-power diode arrays for additive manufacturing. Surat is a company that was spun off from the lab, and they are currently using similar technology, as well as spatial polarization compensation for high average power solid state lasers, and finally, new applications in adaptive optics. Okay, thank you for your time.
Thank you very much for being with us today. We love the presentation. We love especially because you have challenges for the rooms here. We have a lot of people who want to talk to you, who have challenges for you. I would like to give the floor to one person who has asked a question in the chat. I'm giving the floor to Nathan Kaplan from Holo. Nathan, thank you very much for joining today. What's on your mind?
Well, Jose, thank you for giving me the chance to ask a question. Just, I have a bit of experience, not a lot, with liquid crystals, and I remember that the very high fluences, such as 1 joule per centimeter square, and very short pulses, they tend to have problems. You get bubbling and non-linear behavior in them. Have you tried to scale up to these energies and saw that it's feasible?
Yeah, it turns out that the liquid crystal is not the fuse. Liquid crystals have been shown to scale to many tens of joules per square centimeter in the nanosecond class regime. What is a challenge is the photoconductor and the coatings, particularly these conductive coatings that need to be applied so that the voltage in the electric field ultimately can be deployed across the liquid crystal molecules. So those are the elements that we're currently working on to try to extend this performance. And part of the secret is moving to high or wide bandgap materials like gallium nitride so that we can raise damage thresholds, but at the same time maintain high sensitivity.
Thank you. That's a very
Thank you very
interesting
much,
point.
Nathan. We are really interested about these coatings. Today, we would like to know if there are any challenges in particular on these coatings. Is there anything that you would like to ask the people in the room, John, any particular challenge, I don't know, metrology, on the position, on the material, that you would think it would be great to have the question answered in the meeting?
Sure. Yeah. Some of the challenges that we have are particularly in the photoconductors and their scale up. So many semiconductors are, grown for the electronics industry, for the microprocessor industry, but for optics, there's very few. Silicon carbide comes to mind, of course, silicon. But in our case, gallium nitride is very well known for high-speed electronics, for LEDs, for small diode lasers. But to scale them up in aperture brings new challenges of finishing them and producing them at high quality. So that's one of the challenges that we're currently dealing with. The anti-reflection coatings that need to be applied to this device, there's 4 of them, 2 on each of the substrates. Those also become a challenge, particularly since 2 of them also need to be electrically conductive.
When people talk to me about coatings and silicon carbide, I directly always go without thinking, John. I go to Optoman. Lucas, thank you very much for joining today. You come all the way from Vilnius, Lithuania, la new capital of laser technology worldwide. Lucas, can you tell us, first of all, you can help here Lawrence Livermore with this challenge? And second, tell us a bit more of what you do.
Thank you, Jose, for the introduction. Thank you for I was real glad to have you at Optiman today. Yeah, and this specifically this slide actually is really interesting for me because ITO coatings is a new thing that we looked into at Optiman as well. as a possible addition to the portfolio. Let's say we don't have much experience with it yet because it's conductive and not so much related to high power focus of ours. So yeah, maybe the question from my side would be as well. I mean, is this a coating that you experience problems when it comes to damages, and are there any alternative conductive coatings that you looked into?
Yeah, so on these first generation devices that use the ITO, these were operated at low fluence. In the second generation devices that we're currently looking at, we're looking at integrating the conductive coating directly with doping into the surface layer, as well as exploring other options for coatings beyond ITO, of course, that can provide not only the electrical conductivity, but also participate in the anti-reflection needs of the four surfaces here.
Okay, sounds interesting.
John,
Yeah.
Lucas brought a slide. Lucas brought a slide and he would like to share it with us. John and I are desperate to see it. Lucas, tell us what you do.
Okay, yes, let me start my slides. For that, I think John has to exit his view.
I'll do it. I'll do it. Okay.
Okay. Is it okay? You see the correct screen?
Yes, we do.
You
But
hear me?
please
Okay.
go to presentation mode. Yes, perfect.
Okay. So a quick intro that for projects like that, for the high power laser processing projects, the beam shaping is not the only challenge. It was already addressed by John a few times that, there's one major possible bottleneck that actually comes to the optical manufacturers. Because when you move with the ultra-fast laser to average powers with 100 of watts and even kilowatt class integration, and especially when you add high repetition rate on top, you get yourself a real headache to find suitable optics and coatings. Because at that point, laser beams become extremely sensitive to the optical losses and thermal effects. And even the small absorption in mirrors, windows, beam splitters, polarizers, they can introduce heating, wavefront distortion, or long-term degradation. So at Optoman, our role as a technology enabler is to make sure that these laser processes and beam shaping performance survive the full optical chain. And we do that with ion beam sputtered dielectric coatings optimized for high power ultra-fast lasers. And of course, my statement needs a bit of the verification. So I'll briefly show you 3 measurements that we validate our biggest development at Optoman, called the non-degrading optics. So first we have the LADT testing, and our coatings show flat LADT behavior without the degradation slope. So I'm talking about this part. So that means that performance remains stable, and instead of gradually weakening under exposure, it remains stable and works as expected to. Second, we did the endurance testing. So we shot the same spot with the femtosecond laser for 3 hours straight at 0.2 joules per square centimeter in this case, and we observed no surface changes. So this demonstrated that we achieved long-term resistance under repetitive ultrafast irradiation. And third, of course, it goes without saying, absorption testing needs to be done. So we were able to achieve absorption values well below 1 ppm, which enables minimal thermal load and losses, even at high average power. So together, these characteristics help to ensure that beam shape created in the upstream is the beam shape that actually reaches the workpiece. So that's it from Optoman side. Let's look into what technologies does our coatings enable.
Congratulations, Lucas, on everything that you are achieving. John, stay tuned because first of all, Nathan asked a question in the beginning. And for me, it's very important that we understand the challenge of DOEs and the thing needed for them. Lawrence Livermore was very clear on his challenge. Nathan, do you have perhaps a solution or a way that you could collaborate and help him with that challenge?
Actually, I think for Lawrence Livermore is less about us, more about peoples of materials such as Optoman. But I think other speakers in ahead will have, let's say, where there we can offer a better solution. Thank you, Jose.
No, but we have
By
a
the way, we're
slide for you.
working with Lawrence Livermore in the minor systems, just not on this specific line, I think.
Nathan, this was my cue for you to show the slide that we know you have ready for
Yeah,
the
yeah, I
meeting. So
know. I'm
please,
trying to tell you that I want to show it later, but fine. I'll show. Okay, thank you, Jose. So I'll just talk a bit about us, although I think it's a bit early. We at Holo were specialized in beam shaping optics based on mostly on diffractive optics, passive components that are meant to be used in high power and high-end industrial laser systems. We cover everything from the deep UV up to the mid IR, and our DOEs can basically shape an input laser into any desired output shape, including splitting, shaping, even focal manipulation, such as for glass cutting and other types of manipulations of the foci. And of course, DOEs have the huge advantages of being manufactured in-house and at Holor and with using lithographic methods, so they have effectively absolute angular accuracy, unlike refractive optics, and very high LDTs, similar to a flat window made of the appropriate material. And you can combine multiple various shaping functions such as flat top, splitting, etc., in a single surface and get it at the focus of your system, which is what most people in the industrial applications need. Thank you for the opportunity to present that, Jose. And that's mostly relevant for people working in the industry and in various systems such as glass cutting, material micromachining, and even skin treatment.
of course, and Nathan, thank you so much for this. And later on, we're going to have Lasea, and we're going to have Rolomatic, and many of them. But thank you so much for sharing that. John, you heard from Ottoman, from Nathan, you have something in your mind. Is there any particular challenge that you could offer them from the material or from the DOE perspective?
Yeah, I think it'll take some time to absorb some of that, but ultimately we have a lot of laser development, not just the National Ignition Facility, and we take advantage of amplitude shaping, phase shaping, polarization shaping. So I think there's a lot of particularly new frontiers as most lasers have gone to high average power in controlling not only intensity but phase, but also birefringence. So yeah, I'd love to continue the conversation about what we can do in those areas as well.
Stay tuned because there will be a lot of email introductions about this because I'm getting lots of WhatsApp saying, who is this person? I want to connect. His presentation was great. Thank you so much for being here. Stay tuned. We're going to go now to one of the market leaders when it comes to laser industry. For many years, we've been interacting with IPG in many different particular fields. We are really happy today to have at our online industry meeting, Mustafa Koskun from IPG. Thank you very much for being with us today. The floor and the attention of everyone goes to you.
Well, thank you, Jose. It's going to be difficult to follow nuclear fusion, but I'm going to try my best. So can you guys see my slide?
Can you go presentation mode?
I am trying. How about now?
Yes, we see it perfectly. Go ahead.
Okay, great. So we're going to talk about the keyhole stabilization through some of the laser beam shaping that we do, which is we're actually using not beam shapers in this case, but adjustable mode beam fiber lasers. We have as IPG, we have a huge history of innovation that provided industrial solutions to customers in many different applications and mostly high power in this case. Today we're going to talk about some of the particular challenges in the EV components welding. These components usually cannot be welded well with traditional welding technologies, including some of the laser technologies that has been applied to other parts of the automotive industry. These are namely around the battery types, which is the cylindrical, pouch, and prismatic, on the cell or the prismatic battery portion of it, or when you go into packs, electric motors, and all the power electronics, there is a slew of applications requiring very different solutions in this case from this technology. The requirements, the challenges are clear in this case. Everybody wants welding depth consistency, higher throughputs, Spatter pre-process is incredibly important for this type of application. Welds have to be porosity free, heat input has to be low, many other components. Of course, it has to be 100% quality controlled in this case. What we're going to look at is a couple of different things that we do address through different type of beam shapes that we apply to the weld. This is a keyhole that is generated through a weld pool. So if you can, hopefully you guys can see the video that's playing right now. So as the laser beam hits the metal, which requires it makes a molten metal in this case, as the metal molten metal is splashing back and forth, it creates a unstable keyhole, and this unstable keyhole results in depth inconsistencies as well as some of the porosities that are generated through this operation. So what the IPG currently does through beam shaping in this case is to apply a secondary beam around the center beam, which call this the ring beam. And this ring beam actually helps us stabilize the keyhole. This preheats the metal before and afterwards, controls the temperature in this case, and leaves the keyhole open. And so the porosities actually also escape during this time frame. And even the surface contaminations get burned out through this process as well. At the end, you get a much consistent weld from this process. Also, the process ends up with the porosity-free welds in many different processes. Porosity is incredibly important, as well as spatter in this case. The spatter is also completely eliminated during this process as well. There are many different beam shapes that we provide. There's a center beam and there's a ring beam around it, and they're very different types of this are available for different welds. So that was an animation, clearly, right? So what we done is actually went to the European synchrotron radiation facility. This is in France. There's a large X-ray facility that we have utilized outside of Lyon. And so this is where we have actually looked at real time what is happening in the weld pool. So next, you will see the weld from a standard fiber. You can see any standard laser in this case. You can see the depth inconsistency and also the porosities that are being formed. And at the bottom of that, with an AMB laser, with a beam shape around the center and the ring beam, you can actually stabilize the keyhole. I'm going to play this one more time so you guys can see it. So you can see on top all the porosities that are created. And at the bottom, it's almost porosity free in this case, much better depth consistency. You can, from the top, there is much little spatter that's coming out of this process. This is revolutionary in terms of getting spatter free and porosity free results. What we also do is we measure during this time frame what we are doing. So in this case, we have an OCT technology, OCT-based technology, to look into the weld pool and look at any kind of disturbances that you can see, as well as measuring the weld depth through this process. So weld depth measured through another laser beam that we throw into the keyhole, and we measure completely throughout the full process and gives you the full capability in terms of getting quality control. So what you can see this is from a synchrotron weld data and the LDD data, the OCT data that IPG actually collects from this. So you can see it almost perfectly matches the weld depth data from the synchrotron data, the X-ray data, live X-ray data. So this is, of course, incredible in this case in terms of full quality control. So there are some other videos where we can actually show standard lasers versus AMB lasers, where you can look at how you can control the keyhole, how stable of a keyhole that you can generate, which results in no porosities and also no spatter during this weld. Obviously, in battery applications, as you can imagine, it's how important this is in terms of the process results and also how the application results are determined. So these applications are used in both prismatic batteries and cylindrical battery packs. We're going to give you some data on from one of the automotive companies who have used this in their production for many years now. And prior to utilizing AMB lasers, the regular lasers were provided about a 70%-ish, 60 and something percent-ish production yield. Utilizing the LDD, the OCT technology, they could do rework. They can understand that if you not hit the depth correctly, you can rework it and get that to 95% of yield. It's a huge increase in yield. But of course, battery manufacturers are looking for a lot higher than that in yield. So utilizing the AMB technology in the real life scenario, we can actually get to about 90% yield without even rework, just by utilizing the beam shaper that we beam shaping that we have applied with utilizing different fibers in this fiber technologies in this case. And with rework, we can increase to about 98.5 to currently about 99% in this case. Also, the takt time got reduced, quality improved substantially, and many other benefits around this. Just by itself, laser will not do much. So you will have to have beam delivery optics, you have to have process monitoring, and all the connections to the outside world where the customers, robots or PLCs, other things. But we can achieve all of the the solutions that this application requires through these beam shaping technologies and also our fiber technologies that we apply. So thank you.
Thank you so much, Mustafa. I mean, this is really a big improvement in welding. So this is one of the things that we saw last year when we're releasing the laser subsystems with the OCT. And I would like to call Mark because we already got questions coming. So Mark from LASEA. So Mark, could you please unmute yourself and ask your question?
Yes, it's just a short question. Does the optics to achieve this beam shaping is integrated in the laser or is outside of the laser?
Actually, this is a beam shape that we provide with fiber technology. So it's not actually a beam shaper that we utilize. It's multiple different fibers that we apply to this thing. It's a different fiber technology where we have a fiber architecture with a core and a secondary core or cladding, all the different things that we apply. But those are different diameters and different scales in terms of what we apply to the field. So there's no optic that is involved in this case at the moment. But of course, your question is, can it be done with that? Yes, clearly we can definitely utilize optics externally or inside the laser itself to be able to deliver this as well.
So
Okay,
you are
you.
saying, sorry, you are saying that this is more like a refractive with an integrated system. This is what you're saying.
So what I'm
Mustafa.
saying is this is a fiber technology. There are two. There's a core fiber. There's a cladding. There's a secondary cores that you apply this. There's no actual beam shaping optic that is involved. But
Yeah.
of course, this can be utilized through a beam shaping optic as well. The same effects that we'll be able to see.
So what is the major challenge right now for
Major
like you?
challenges in welding is that we have shown is of course that you want to make this even better. You want to make more customized solutions for the customers who have different challenges. In this case, you can have different thicknesses, different materials from copper, aluminum, and different types of that. Requires very different technologies to look at and the very different beam shapes to be able to apply to have a spatter-free and porosity-free welding.
So is it possible to, or is it easy way to do like customize somehow
Absolutely.
for example for core to ring ratio or for temporality stability?
Exactly. Those are the challenges that we have in customizing into a certain application, that the iteration time and all of this can be also improved in order to be able to find out what's the best what's the best fiber architecture that you have to apply to this.
Yeah, and then this is something that it could be like, you know, like if I think clear, in a lot of other industries, not only for EVs. It's like
Of course,
aerospace or
definitely.
yeah,
Yeah, definitely. We
it's
apply in a lot of
the quality.
medical areas. Medical welding
Mm,
requires a lot of these as well. But not only in welding, right? We also have industrial cutting, industrial additive manufacturing. Those are all the
yeah,
areas that beam shaping is required, whether through fiber technologies or through usage of diffractive optical elements or other optical elements that could be used. And glass cutting, as Nathan mentioned as well, is one of the other
hmm
areas that is in industrial processes that requires beam shaping actually to be able to do a good job. So
yeah. Okay, so let's imagine that you are going to use optics. Okay,
yes,
so what kind of optics will you think you will use?
we will need optics that are high power handling.
Mm-hmm.
We will require optics that will be programmable in terms of to be able to make
Yeah,
different shapes through this
yeah,
thing. So that's the challenges, and of course, iteration time is quite important. So you have to be able to. We do not have 6 months to come with the next level of complexity and then
yeah,
test that in the lab. That will be a very long iteration time. So it has to be much shortened uh, in
yeah.
terms of producing
Yeah,
these
so
things.
this is actually very good. So I would like to get the opinion on Sebastian Henkel from Asfericon, because if someone knows how to do the optics for this kind of things is Asfericon. So Sebastian, could you please tell us what do you think about it?
Yeah, so it's a trend we definitely see on for high power laser applications, and you might get an idea, probably not during the presentation I will hold today about the high power laser applications, but in general, I can say if it comes to beam shaping, then it's definitely worthwhile to think about the materials and the whole optical design which can be used in this arena. And I think there's already some exchange going on with IPG. At least it was the case a couple of months ago. So yeah, there's something coming up constantly from our side, and yeah, it's definitely focusing on high power laser applications. And the iteration time is quite small, so I think within a couple of months we are able to produce different shapes in the focal plane or with a stable propagation length. So yeah, just let us know. So it's a big variety of different elements we can provide, and we can combine with each other.
Actually, Sebastian, I mean, Asfericon is they know how to translate the beam shaping designs into manufacturing decisions. So would you
Yes,
please share your slide and tell us about Asfericon?
yes, of course. So, so you can see my screen, right?
Yes, not in presentation mode yet, but soon. 3, 2, 1. Yes,
Is it working
crystal
now?
clear. Yes, yes, yes. Perfectly good. Oh,
Okay.
came back. uh, okay, now it is. Yeah, there is a little bit delay always for.
Okay. But now you can see it, right?
You lose the presentation mode, so if you go
Let's
once more, yeah.
Okay, so let's go ahead. So yeah, so about beam shaping in general. So I brought some ideas of what we are currently doing with a nice R&D project. And as you know, we are mainly doing beam shapers for the focal region, which can be basically used with a focusing lens. Can be any type of a circular or square or elliptical shape. And then on the other hand, there are beam shapers in a collimated beam which have very long, let's say, propagation distances up to several meters. And as let's say outcome for what we have seen in the market, there will be a fiber coupled version coming up quite soon. And this was mainly driven by a project which you can see here on the right-hand side, which is basically quantum gravimetry project where the task was to generate a very stable propagation length with a very stable wavefront, because what happens here in the application is that we want to determine underground resources, just as water reservoirs, mines, or let's say oil and gas reservoirs in the earth. And therefore, we are using the top hat beam shaper. And in this case, why does it matter? Because you want to use a top hat profile over a Gaussian profile in order to determine the atom cloud diameter, or the atoms which basically fall down here, and you want to capture those single atoms and want them to have interacting with light. And if you just use, let's say, a Gaussian beam here, you would probably only carry or catch the ones in the middle, which will increase the noise ratio, and in the end will not generate a very nice measurement result. So that's why we came up with a top hat beam shaper as an athermal system, because this one has to work in very harsh environments and very demanding temperature environments, changing temperatures. And in the end, to give you an idea, what's really done here in this quantum gravimetry thing is we want to determine the ninth decimal point of the G number, and to get an idea. So this one is only showing the seventh digit here, which can be used in order to determine big buildings and stuff like that. But you really want to look something which is underneath the earth and far below, and that's why this kind of instrument is used here in this application, and it's a very precise athermal system which is used in this kind of R&D project. So it's a very special application apart from what we are usually doing if it comes to laser welding, laser cutting, all those things.
So excellent. Thank you so much, Sebastian. I mean, this is really great. So I want to go back to Mustafa. So we are having a lot of questions that they are coming in private, and there is one, and also on YouTube. So there is one that I have to read because it's not possible it's not in the room, but it's to Mustafa. So is whether have the idea to use the temporal pulse shaping method as well, besides the spatial shaping. So Mustafa, what is it?
Yeah, so these are currently CW lasers, so there's no real pulse shapes in this case that are being applied, but there are other applications that will require some temporal pulse shaping as well. This is more on the cutting side, especially if you talk about some of the glass, plastic processing, some of the other processing areas. We have not seen the temporal pulse shape really affecting too much on the weld process itself at the moment. It's more of a time and heat management in this case. Mostly that's the key, the things that we have tackled.
Yeah, absolutely. Yeah. So also, Nathan, I know you have another question. So Nathan, can
Yeah.
you mute yourself?
Thank you, Elena. So, Mustafa, if we go back to the welding system, these sorts of core clad fibers have a larger divergence than a similar multimode single core fiber by definition, because they have a bigger shape. Does it mean that you have to use larger focusing optics, such as an F theta, if you're using scanning here, or just an objective, compared to what you would need if...
No, not really. That requires, because there's a collimator that collimates the beam. So there are you actually collimate the beam at a certain height, right? So that determines the beam size that you would get. That ends up with a certain magnification when you use a collimator and a focusing lens, whether it's a straight welding head or a scanner solution. So that still there's a magnification associated with it, and that magnification provides you that theta lens provides you the field size that you would get. So you actually work the problem backwards to understand where you have to be in terms of divergence and other things as well. So you can actually solve the problem across multiple levels if you have to. Of course, there is the laws of physics that comes in the middle somewhere that you cannot overcome.
Yeah, what I'm trying to say is that like since you're starting with the beam already shaped at the fiber exit, this is basically imaging the fiber face to the work surface.
Pretty much.
Then you need all your optics to contain this larger field, including the collimator itself. If you could do the shaping really close to the focus optics after the collimator and not as part of the fiber, you would not need such large optics. Yeah. Because now you need to collimate a ring and the central spot with a certain diameter. Anyway, this is a bit technical. I'm not sure it's for this.
We can discuss that at a certain
Yeah,
time.
that's
But
a separate
we have
discussion.
not seen that kind of issue at the moment. And large optics actually kind of helps you with the power management as well when you have really high
That's for
power.
sure.
So there's another story there. Yeah.
And we are very happy that to put you in contact, because this is actually what we do. So
Yeah.
please, but I mean, both of you are right. It's like I got on my experience. So you were saying about programmable, right? And there is someone that is coming. I would like to call Paul Busk from Fraunhofer ITL and from Arnhem University. And this is going to be a very interesting project that they are working right now on. So Paul, please, the floor and attention is all yours.
Thank you very much. Yes, I have a bit of a different working point because I'm mostly a researcher, so I don't have a company and I don't want to sell anything, but mostly I want to sell dreams. So I'm going to present a little bit of our work on laser beam shaping with diffractive neural networks for the application, in this case, of USP processing. So briefly to go about the core idea again, what is a diffractive neural network? Maybe some of you have already heard of it, depends a bit on the application. The idea is to have a physical realization of an artificial neural network. So then you treat light as your input information. You have face mask as layers. And yet then you can treat like the pixels of each face mask as an equivalent to a neuron. And such a network then enables image processing at the speed of light. This was already investigated a few years ago, so it's nothing new. And this can be then experimentally realized with diffractive optical elements. I think Nathan is the expert there as well, or spatial light modulators. I mean, there are several people here as well who work with those. So if you then design such a network, and here I have presented an example where I have light in the shape of a handwritten digit, in this case a 3, then I can train this network in a computer. And if I now simulate the light propagation from the input plane to the detector, I can see that I get a diffuse diffraction pattern where I will get the majority of the intensity in the 3 detector. So I got the correct label. But we're not working with the image processing part. We are applying this to beam shaping. Basically, it's a very similar setup. It's just the other way around. So I have an input Gaussian beam. I have one or multiple diffractive layers. And then I can define several target planes with intensity distributions I would like to realize. And this is an example configuration with 2 layers and 2 target distributions. And this has some nice properties that are very advantageous. We can optimize for both the amplitude and phase. So for example, for a large top hat distribution, we can also create a collimated top hat distribution with a very long depth of field. Especially when working with spatial light modulators, it's convenient that we can correct some deviating effects that occur in spatial light modulators. For example, the pixel crosstalk. You have some interactions between neighboring pixels and SLMs. We can consider this already during our design and then correct this in our measurements. It's in the focal plane, it doesn't always work perfectly because we're still physically constrained. But if we go to planes outside of the focal plane of the lens, we can get extremely high beam shaping fidelity. And then we can use multiple multiple target planes to get effective three-dimensional beam shapes. So here you can look at the bottom row, because this has corrected all the deviating effects of our two SLMs that we use in the setup. And we created a light cuboid, which has like an edge length of 300 microns, but a depth of 20 millimeters. So this is a very significant increase in depth of field, which you would get compared to conventional beam shaping methods. So this is basically the fundamentals, but we also have some additional benefits. We can train these to be robust against misalignment, basically in the same way that we can train a neural network to recognize variations of the same image to the correct detector. And since we're using neural network architectures, we natively use GPUs, and it's very straightforward. It's not a lot of difficulty. But when we go to the processing, often also the companies and the people that want to apply beam shaping ask which beam shape is actually beneficial for a given process. I mean, the donut is often tried out, a top-hat distribution. And if we look to thermal processes, continuous wave processes, one can physically solve this, and this has been already done temporally and spatially to get solve the inverse heat conduction problem, and then you get so-called armchair intensity distributions that create a uniform heat pattern. But when I look at USP processing, the physics is a lot more complex, which means that getting an inverse physical model of the USP ablation process is quite costly, and it's very sensitive to the material, the pulse duration. You have so many parameters, so it's very costly. Alternatively, you can get a machine that just iteratively learns a proxy model of this ablation process, and we've implemented this using Bayesian optimization in very close collaboration with the Chair for Laser Technology. So the idea is we have a fully automated laser machine. In this case, a microservice controls the system, so we can control everything fully remotely. And now we have also an inline metrology system. So the machine can automatically measure the surface profile with a white light interferometer and lots of different sensors. So we make a shot. We get the surface data and evaluate it for a metric that is important to us, and put this result into our Bayesian optimization-based inverse ablation model. Based on this, the algorithm calculates a new beam profile that we would like to try out. We design a phase mask or phase masks for this based on our diffractive neural network architecture. Then we put this on our SLM setup and go back into the laser process and get a new shot based on this, the biggest improvement that we want to have. And this is basically the Bayesian optimization algorithm. So when we do this, we get, for example, an optimization pipeline like this. So we start with a very low optical efficiency, ablation efficiency in this case, and iteratively we try different parameter combinations for our beam shape out until we reach a point where we say, yeah, okay, the algorithm converged mostly. And then we get such an experimental optimal intensity. It's kind of a top-hat with brighter edges. It's not the most surprising result for such a metric, but the nice thing is that it doesn't have to be only the most simple metric or the most simple parameters. We can modify this for arbitrary optimization targets. For example, you can also use this to optimize the surface roughness or whatever parameter is important for your process. So then you can tailor this process to find actually the beam shape for your specific process that actually works best. Beyond this, we are also using our beam shaping approach for optical stamping. This is in the so-called project Metamorpha, an EU-funded project in close collaboration also with LASEA. I think they might show some slides of this as well. I will just show a brief example of what we're doing based on the stamping. So the idea is we have a machine, an optical module using two spatial light modulators. It has a bit of a convoluted beam path for spatial reasons, and a theta lens. And then we can create an intensity pattern. Here, this is a measurement that was done at LASEA. And this is a unit cell that we shot with this laser, so in a single shot without scanning. But we can scan now this stamp in periodic patterns. And this leads to a reduction of process time at this point at 81%, but it depends, of course, really on the applications and what power you have available, what your beam shaping system is capable of, but there's a lot of potential. So in general, we have some novel flexibility to three-dimensional beam shaping with our diffractive neural networks architecture. And this self-learning USP process now solves or can be one aspect of solving this issue of determining actually the beam shape that you would like to have. And this optical stamping might drastically increase the processing speed for USB processing. So here I brought a slide video, of course, of a measurement where the beam develops along my optical axis. So we can see, yeah, I get this caterpillar pattern. And I can also, in the same beam without switching anything, get this butterfly shape as well. So and the next, we need to explore further this automatic process determination. There are more parameters, more variations. There will be some scientific publication in this year. And we are also currently, so far, we have mostly for ablation experimented with the two-dimensional shapes, but the three-dimensional beam shapes are, of course, one aspect where there's still a lot of potential to be explored. So yeah, that's about it from my side. I'm happy to take some questions.
Thank you very much for being here today, all the way from beautiful Aachen. It was great. It was really great. So during your presentation, I reached out to one company I met at Photonics West. It's called Silicon Light Machines. So I had a great chat with them and with the Katana platform. And I wanted them to comment because they have ultra-fast MEMS-based SLM solutions. Gregory Jacob, thank you very much for joining the meeting today. Gregory, just unmute your microphone. Yes, this meeting is not for shy people. We just do that. We welcome people in the room. Gregory, could you tell us, for people who don't know the ultra-fast MEMS-based SLMs of Silicon Light Machines, what you do, and then you can ask the question you have in mind?
Yeah, we make phase modulators or amplitude modulators. The refresh rates go up to about 350 kilohertz, so quite a bit different than the LCOS modulators. I was just curious, in the Metamorpha system, is the beam Gaussian on the first spatial light modulator, or
yes,
do you use some beam shaping before that?
No, it's just a Gaussian on the first modulator.
Okay, thanks.
You're welcome.
So one question for beautiful Fraunhofer ILT. Whenever I go there, I'm amazed by the kind of things that you do. Is there any particular beam shape that you still are struggling with? We normally talk about donut shape or Gaussian shapes. Is there any particular challenge that you have here for the beam shaping industry?
I mean, so right now I would say there's not like one specific challenge. There's always basically the request is to have the largest pattern that you want to have with the smallest structure size. And then at some point it's like, well, it's there will be some physical limits. Also with the available power, if we're working with the SLMs, of course, if we're working with DOEs, then these problems get significantly reduced. But still, if I want to be close to the diffraction limit in the structure size, and I would like to have a 20 times 20 millimeters pattern, then I will get to certain limits that are, I would say, physically limited and not optimization limited. I'm sure Nathan can talk about this for hours as well.
Nathan, you are nodding along, and we want you to comment because I think you have something very big in your mind.
Actually, I agree. The limits on such systems, especially stamping, are mostly power limited because in shaping we can do almost everything. Power and NA limited. Yes, and of course field limited, because and that is a matter of the F theta producers, which we don't have here today. But generally, all these problems can be solved other than power. Because when you want to process a 20 millimeter area, that requires some very tricky processing schemes. But still, the front line is always pushing forward. I mean, we are reaching rates. I see our customers reaching rates that are quite high, approaching 1 meter square per minute, etc., in some stamping applications, and even further.
1 meter square per minute.
Yeah.
What application is that?
Yeah, that was I think in the previous Prometheus project, which we were part of, it was in metal texturing for various tribological applications.
I have another person that wants to contribute to the conversation, Dirk Hauschel from Optica corporate member Focuslight. Dirk, what's on your mind? I think you have some questions here.
Yes, thank you, Jose. A question for Paul. So thank you for sharing this nice setup and the options to manipulate in a dynamic way with spatial light modulators. My question is how sensitive this setup is for variations in the beam shape coming out of the laser, because when we run a laser at lower power, you have a different m square than the high power. how sensitive it is, and do you have some methods to compensate this?
Yeah, thank you very much for the question. Yeah, it's a really good question. It depends, I have to say. That's the nice thing of this design architecture. If we already know that there are some uncertainties that we cannot determine, or we know that there are some variations in both aberrations and beam profile, we can already account for them to a certain degree. It's not magic, but we can account for them. On the other hand, of course, we can also do a calibration with the SLMs directly. So basically, I look at the beam profile that I got, the measured beam shape, I see there's a deviation. I can infer what the deviation caused, and then I just can correct it on the SLM. Yeah, but depends a bit. If you have like strong variations, for example, in the M square, like if you just leave the coherent plane, then there's of course limits, because this is a coherent beam shaping system, so you will get some blurring or some different effects. But if it's just like aberrations and beam deformity, then we should be fine.
If we're having an Optica meeting on laser beam shaping, we need to give the floor to Kylabs. I am really amazed by their job, by their progress on the last years, how everybody knows MPLC technology now. When Palier, we got the request of very different beam shaping solutions so far. Any challenge that you can overcome? Anything that comes to mind? Tell us what you do.
So can you hear me first?
Loud and clear.
Okay, perfect. So I know that we have to be very fast. I was already sharing my slide, you see, Jose. So
Go ahead,
somehow
ultra fast photonics.
no, I was ready, you see. Yeah, I tried to be at the same speed as you, actually. So actually, okay, let me answer for one point. There's been a lot of challenges which have been mentioned, and I had comments on a lot of them, but again, it's always a long answers. So at least, thank you very much, Focuslight, for making such a perfect introduction to what challenge I want to solve, which is exactly what you were mentioning, stability of the beam, which I believe is a huge challenge. But on the other side, I want to say that Paul was actually mentioning another one, which is the other trade-off that you have to make. So reaching diffraction limit, which basically, by the way, may not be the D of diffractive optical element doesn't mean you reach the diffraction limits. It's just that you use diffraction to make the shape. But nonetheless, it's true that if you want to reach diffraction limit over a large field of view, like 20 millimeter is huge, it's somehow just impossible, because the numerical aperture you would need to have makes the optics more expensive than the whole machine. So there are super cool numerical aperture optics used for crazy systems, like in semiconductors, but I don't think anyone in the room can afford that for their machine. So that's one challenge. But if you don't mind, I think that I want to reply with my slide on the challenge of beam stability.
Go ahead.
Shall I go for it?
Yes, please. Presentation mode.
Okay.
And
So now my slide, is it full screen?
yes.
Now it is.
Okay, cool. So thanks again to Focuslight for the very nice introduction. So Calabs, as you said, Jose, we are working on beam shaping, and actually, to be really exact, we work on beam manipulation for a lot of time right now. But when it comes to beam shaping and laser processing, I wanted to highlight one stuff, which is what we do for microprocessing. And it all started by that problem somehow that was perfectly introduced just now. When you want to do beam shaping of a monomode laser, which is the case of femtosecond laser, they are monomode, actually it's extremely sensitive to any instability, meaning that it's the same for any technology in the world. If your beam is moving, somehow your shape is not stable, as you can see just here. So basically, when we started to work on that, we said, okay, then if we want to have a nice shape, we need to stabilize the beam first. So there are active ways to do it, but they are very limited in terms of complexity, safety, and price. And somehow we really used our core technology to invent some unique way to stabilize the beam. So it's called mode cleaner, because we are cleaning the beam, and it's based on mode manipulation. So I will really insist, it's purely optical manipulation. There is nothing moving, there is no piezo, there is no SLM, there is no moving mirror, there is even no electricity going into that system. 100% passive, 100% optical. So when we have a beam which is entering our system, there is kind of a mode analysis which is made of that beam, and we let the main mode, the Gaussian mode, go through the system somewhere, and all the other modes we try to have them going somewhere else, so around the main mode. And then somewhere in our system, there is something which is blocking them and dumping them. So it means that we only have the Gaussian mode which is going through, which is what you see just now. Why is it useful? When your beam is shifting, for example, for us, this shift is more energy in a higher mode. So it's going somewhere else and it's dumped. So we are really dumping the shift. I'm really not kidding. We are dumping it. And the beam is not moving at all. In 3 dimension and in shape, we only have the Gaussian beam going through. If we have a beam which is elliptical, it's the same. We are dumping the ellipticity and only the Gaussian beam is going through. So it's pure stability in 3 dimension and in shape, again, one more time. And that's super important when you want to do beam shaping of monomode femtosecond lasers, because you have instabilities everywhere. So especially when you go to higher power, you are always somehow having thermal effects in your lenses, in your mirrors. When you change the frequency of your laser, the waist is moving, and all that is uncontrollable somehow, only if you use this beam stabilization. And actually, we did it. That's the main result. That's an example of measurement in a very industrial, precise environment, controlling temperature and all that. And that's just the stability of an output beam of a very beautiful, stable industrial laser. It's actually a Monaco laser from Coherent. And that's the beam stability with and without our technology. So you can see that we managed to have a pure stability of our beam. And then I just want to say what is the use of that, and I think that I will run out of time after that. So one of the use is to have a clean laser, for sure. You can just put it at the output of the laser, and the laser would be much more stable in terms of position, but also in terms of shape. It is super useful to have beam shaping. So that's actually the only way to have a pure beam which will be never moving in any condition in your process plane, no matter the power you are using and how you are tuning the different parameters of your laser. It's also useful if you want to have 3D shapes. So 3D shapes are pretty cool. So I saw that there were a lot of guys working in glass in the room today. Well, if you want to have these 3D shapes, which are useful to cut glass, they are extremely sensitive to misalignment. So one more time, if you stabilize the beam before shaping it, you make sure that you maintain your 3D shape with the profile you want in any condition. And the last one that we are really heavily working on right now is fiber coupling. So the idea is to make a very safe coupling into hollow core fibers, because right now the laser in ultra-short pulse world are mostly free space, because somehow the fibering is not that safe, let's say, and we invented somehow a way to make it absolutely safe. In no condition you can damage a fiber. So since I'm running out of time, I will stop there. And that's the name of our product, Canada USP Pure Beam. It's really a way to do beam stabilization. And typically it can be really super useful for fiber injection. So was I fast enough, Jose?
You were ultra fast and brilliant. And when it comes to glass manufacturing, Gwen, I think you know the people I'm going to call now. I always do. When it comes to glass manufacturing, especially large plate laser marking, I always go to Liège. I go to Liège, I go to Belgium, I go to the company LASEA. Mark the culotte. We always leave the best for the last. Please let us know what you do. Let us know what the systems of LASEA do, and most important, share with us some of the key challenges for people in the room. The floor and the attention of everyone goes to the very beautiful city of Liège.
Okay, thank you for the kind introduction. I will share my screen. Oops. And in presentation mode. Okay. So hello everybody. I'm Marc Descouteaux from LASEA, and I will present you the following subject: beam shaping in the industry. And I will start with a short presentation about LASEA. LASEA, it's 6 sites around the globe and 4 production sites to produce our laser machine tool with a specialization with the femtosecond laser. And inside of our group, we have a lot of competencies about design, mechanics, optics, software integration, and I don't see all of my screen, but it's okay. Just okay. And now I will speak about our motivation, why we use beam shaping, why we start to use beam shaping in our machine. It's because the current situation, actually, generally, we have one head machine with a femto, with one head scanner machine with a f theta lens, and only one Gaussian laser femtosecond beam. So here we work with femtosecond. Generally, the spot size is between 20 and 80 micron, and we have standard laser energy around 200 microjoule. Actually, we are able to go higher. And it's thanks to that, we have a possible fluence around 100 joule per centimeter square on the samples. But generally, for many quality processes, the fluence, just a few joule per centimeter square, it's enough for good quality processes. But with this kind of machine, we're able to achieve the need of the industry, and we're able to make a lot of different applications. I will not speak about all of them. Don't worry. But what we can do if our customer want an increase of productivity. If we want an increase of productivity, one solution that can think it's more power, but more power with a Gaussian beam and only one beam in the machine is not really interesting, as I said earlier. So beam splitting is an interesting way, and multiple heads too. Multiple processes with one machine is really interesting, but one good solution is beam shaping, especially also for the multiple processes with one machine. I just search. Okay. And I will give you some example of integration of beam shaping in our machine. And I will start with the MetaMafra project. Paul also asked about it. And in the MetaMafra project, so we have SLM, spatial light modulator. And thanks to that, we have an adaptive beam shaping that it's really interesting for the aspect of to be able to make multiple processes with only one machine. And in the case of the MetaMafra project, so we have two SLM, and thanks to that, we are able to achieve, for example, a more stable top hat. So it's like to have a bigger Rayleigh length in a machine that it's really interesting when, for example, you have a non-flat samples. So we have a lot of applications of this machine, and we have different kind of a beam shaping, different than the ones that Paul presented before. And we integrate it in an LS5 machine. And the advantage of beam shaping in this case, it's thanks to that we are able to go faster, so to have more productivity, biggest Rayleigh length, so more homogeneity, and we're able to achieve multiple processes with only one machine. That's really interesting for customers. Another example, it's with a module from Kai Labs. So it's more beam splitting than beam shaping, but it's in only one scanner head. So we have nine beam through the scanner head. And thanks to that, we're able to go faster for a lot of different applications. So we integrate it in the LS lab. And in this case, the only advantage is really faster. It's 9 times faster because we have nine beam. Another example, it's for microfluidics. So here, it's an example of welding of transparent polymers for microfluidics. So, and here you have a comparison between a Gaussian beam, welding with a Gaussian beam, and welding with a top hat beam from Kai Labs module. And as you can see, it's really cleaner. The quality is really improved. We go faster, true, already, 9 times faster. But what was really interesting is the quality. The cleaning of the sample is something that is really important for medtech. and with still a strong welding and even a stronger welding. And as you can see here, we have liquid going through our microchannel produced with our machine. So we work on this project with the LS4 machine, and here the advantage of beam shaping is also faster, so more productivity. We have cleaner samples, so it's high quality, more precision, because as you have seen, as you can see here, the welding seam, we have more precision about the size, the dimension of the welding seam, and we have stronger bonds. A last example, it's also with the Skylab's module, with combining the beam splitting, beam shaping, and the cleaning parts. And we are able to adjust the size of the top at a square. And we use it for a project for drag reduction for the aeronautics. And we achieve a good result of drag reduction of up to 2.5%. And that's huge for aeronautics. And we integrate this system in our Neo machine. So I will finish my presentation with a outlook, and I will speak really fast about other projects of beam shaping, and especially the Syntax machine. Here, it was daily pattern with a 3D machine. The glass project, we have in one machine one bezel beam on one with one scanner head and a Gaussian beam on the other scanner head. So to conclude about all the advantage of beam shaping, it's generally it's faster. That's what we observe all the time. Thanks to the beam shaping, we're able to go faster, so we will increase the productivity. And for the other advantage, it will depend on the situation. So in the case of the Metamorpha project, we observe biggest relay length. With all the adaptive beam shaping module, we are able to have multiple processes with only one machine. So it's something really interesting. And in the case of a microlab project, we observe higher quality. It's like in the presentation of the EPG about the advantage of beam shaping for welding, and sometimes we are able to achieve more precision. So thank you for your attention.
Thank you so much, Mark. So this is a great example on how the corporate members work. So this is LASEA is helped by Skylabs and Optoman. So is a good triad. So we have several questions here. So I would like to call Dirk. So Dirk, you have some questions. Dirk from Focuslight. So could you please unmute yourself?
Yes, I have a question for Mark, and thank you for your presentation. I've just seen some specifications concerning the resolution or the accuracy of bringing your structures on the targets with ±5 micron. Do you see a possibility based on Galvo scanners to improve this resolution or reproducibility in the future? I'm looking on targets below 1 micron resolution, for example, with scanners.
You speak about the resolution of the beam shaping?
Yeah, and in combination, beam shaping in combination with the scanner, because of course, if you go through the field, then you have always a feedback coming from the f-theta optics and the wavefront from beam shaping, so that you cannot address exactly the position that you want to address. And I think the resolution right now, you mentioned about 5 microns, and the question is how to stabilize this to go to the micron level or even below.
Yes, it's a complicated question. It's a complicated subject because the precision of our machine depends also on, for example, of our axis or system of axis, because we make a lot of calibration the calibration of our lenses, the calibration of a lot of our systems depend on the precision of the axis. So if we want to continue to improve precision in our machine, it's something that it's important for us to have more precise axis. So yeah, I don't know if I respond exactly to the question, but yes, improving the precision in our machine is still something that's really important for us. But yeah, it's a difficult subject.
Yeah. I'm fully aware that's a challenge, but I'm just addressing the question because that's also something that is interesting for maybe everyone here in the meeting. And one more question to Gwen, since you mentioned that the filtering of the mode and the stabilization, does this work only with gas lasers or also with fiber lasers? I'm thinking about multi-kilowatt fiber lasers that have a strong change in the evanescent field when you go to higher power levels because of certain percentage of gain-guided power in the fibers. Does this work for these type of lasers as well?
In principle, yes. Still, the idea is that we keep the main mode, which is Gaussian. So I would say that if you are with a beam which is too far from being Gaussian, in the end, you dump a lot of energy. So I would say that the real use of mode cleaner is really made to make close to monomode laser more stable and more monomode in a way. So I would say that with CW lasers, there are a few very good lasers which are very close to monomode, and it would work for that. On the other side, we didn't find application in doing that for now, for the one reason that those lasers are generally fibered. So since it's not free space, it's much more stable because the fiber delivery is close to the process and is already very stable. So the main use for now that we see, but to be honest, maybe 5 years from now, I will change my mind. But the main use we see for now is really on the ultra short pulse lasers because it's a free space laser and it's very sensitive to any thermal effects, thermal lensing, stuff like that.
Okay, good.
Yeah. So we have also Adam Fennis from AMP Optics. So Adam, could you please unmute yourself?
Sure thing.
Yeah.
Hi. My question was about the beam shaping and related to the rings that the IPG was showing with their modes, and then focusing on the light as well. Nathan responded with that it could be done with the hollow ore. Is there any other capabilities out there to do this as well? Hollow ore flexi shaper. Sorry about that.
So the flexi shaper of Hollow can do it. I believe that Sebastian Henkel from Sphericon, he can do fantastic ring shapes, and also definitely Gwen Pallier from Kylabs also does great ring shapes. I am quite amazed by the beam shaping technologies from Hofer ALT, and I actually have seen rings. So anybody who would like to comment on that, but there are many people in the room that can make great rings. Sebastian, would you like to comment, or Gwen, or Paul, or the three of you? Go ahead.
I can comment. I mean, from the design perspective, it's not super challenging, I would say. It's depends more on the fabrication challenge. And I would say then they're both Hollow or Kylabs or whoever is, I'm sure all of them are capable to do something like this. Depends a bit, of course, on the specifics.
Sebastian, your 2 cents here.
Yeah. So I was about to chime in. So if it comes to, hexagons, ring beams, things like that. So we would love to have a look at this, and I think we can help them.
Okay.
Definitely.
Thank you.
Gwen?
So yeah, on the ring dot, actually, there are a few products on the market. Hollow we are also doing it, if I'm not wrong, to just name our competitors. Power Photonics also is doing cool stuff on that topic. So I would say that, it depends what you need. I made a long reply in the chat, but I can just say it. In a way, you have more flexibility doing it in the laser because generally these are dynamic stuff, so that you can adjust the power in between the ring and the dot. On the other side, there is also more flexibility in doing it in a static way because you can do any shape. So right now we investigate a lot the interest of having, I would say, more complex ring dot, meaning keeping a very small dot in the center but having a larger ring. We have investigation with the FSW in Germany on that, on welding. So I would say that I guess nobody has the answer yet. What is the best? But as a matter of fact, there are many ways to do a ring and a dot.
Appreciate it. Thank you.
I would like to first say that for very complex optical system design, I always go to AMP Optics, Optica Corporate member. They are really great. Adam, thank you very much for joining. That's first.
Thank you.
And second, we started on time and we finish on time. Allow me to close the meeting for the YouTubers. And then those of you who want to stay for a drink afterwards, you can stay and we can have a private discussion. But allow me to close the meeting now.
This is Optica. This is lighting